Alright, in this video I'm going to finish up the section 1.3 by talking a little bit about cardinality and what we mean by the cardinal number or cardinality of a set. So let's start with the definition. When we say a cardinal number of a set, we're generally referring to the number of elements in the set, but to be more specific, let's talk about it in terms of this set, which you'll remember is 1, 2, out to n. And the cardinal number of that set is n. Okay? Now, so when we refer to the cardinal number then of other sets, we're going to refer basically to the idea of two sets having the same cardinal number. Another way of phrasing that is to refer to them as being equinumerous. So two sets, A, B, are said to be equinumerous if they have the same number of elements. But remember, we don't really talk in terms of number of elements, we talk in terms of our bijections. So if and only if there exists a bijection from A onto B. If that's the case, if we can find a mapping that's 1 to 1 and onto, then we'll say those two sets are equinumerous, and we'll use this notation to denote the cardinal number but then we will say the cardinality or the cardinal number of those two sets is equal. Now, if A is finite, then the cardinal number of A, which again, sorry about that, of A, denoted by this symbol, is the number of elements in the set. And the reason that's the case is that, as we talked about last time, if we find a mapping from this onto A, then, and that mapping is 1 to 1 and onto, then as a result they'll be equinumerous. It also means that the number of elements in the set happens to be A. That's what we mean by definition. Now, if A is infinite, that is not finite, then the cardinal number is said to be transfinite. So we're going to be distinctive here. We refer to infinite as the type of set that does not have a bijective mapping from n sub n, for any n, onto the set. And now the cardinal number, we're not going to talk about numbers as being infinite, we talk about sets as being infinite, but the number of elements in the set, which we think of as cardinality, as the cardinal number, is called transfinite. Okay? So, what about the cardinal number of a known infinite set namely that set which we refer to as denumerable? Remember, that means countably infinite, and that is denoted by a Hebrew letter that I'm going to write very poorly throughout the rest of this lecture, and I'm sorry for that, but it's actually the first letter of the Hebrew alphabet. Yes, this is the first time we've left the world of Greek letters or derived symbols, and now we're using a completely new alphabet, and it's Aleph null. So I make two little squigglies and a diagonal line between them and give it a little circle up top to represent null. So this is pronounced Aleph, A-L-E-P-H, and then the little circle means null. That is the first, as we'll discuss later, the first transfinite number, which means essentially the number of elements in this set, that is all natural numbers, so we're going to refer to as Aleph null. Now keep in mind that this type of number here is a cardinal number. Now we've used notation for infinity in other classes before, not in this class, but you'll recognize this symbol, the sideways 8. Why don't we use that here? And the point of distinction to be made here is that this over here is a representation of the size or number of elements in the set, whereas this infinity does not mean that we've counted up or collected a group of objects and denumerated them. Instead, this always is in reference to the sideways 8 infinity is something growing without bound. For example, you talk about the limit as n goes to infinity when you're looking at a sequence, or the limit as x goes to infinity of some function. That, in those cases, means you're letting this thing, this mathematical object, grow without bound, which is not the same thing as counting them up. Alright, so with that said, I'm going to pause for a second. Okay, so I'm back now. Let's consider, for example, the set E, which would be the set, let's let it be E for even. My question is, how big is the set of even numbers? So the claim I would like to make is that the cardinality of E is actually equal to the cardinality of the natural numbers, meaning it is the same size as the set of natural numbers, which may seem like an odd claim, because think about it. If you have the set of natural numbers, right, all the even numbers are every other number. I gotta be more careful. So on the top row, I'm circling every single number. On the bottom row, I'm circling only the evens, but you'll notice that I am actually forming a bijective mapping of the natural numbers onto the even numbers, right? Bijective in the sense that it is 1-to-1. Every element in the e's is mapped to by one and only element in the natural numbers, and it's onto. Now, of course, we are leaving out these numbers, but remember, they're not in the set E anyways. So this mapping that I've just created here, if I were to call that F, is in fact a bijection, which means these two sets have the same cardinality. That is, they are equinumerous. E and N are equinumerous. It's a little counterintuitive, but if we define two sets as having the same number of elements, if we can form a bijective mapping, then voila, they are the same size. Which means, by the way, that E, of course, is denumerable. We know that it's countably infinite, but it's the same size then as the set of natural numbers. So note, I was going to write something there that I'm not going to write now. Note, Aleph null is equal to the size of natural numbers. We already proved, by the way, that it's the same size as the evens, which, by the way, would have the same reasoning as being the same size as odds. And if you'll remember earlier in class, we said that n cross n was actually denumerable, which means it is also the same size as n. That is, the set of all ordered pairs whose elements or coordinates are natural numbers is the same size as the set of all natural numbers. All right. Definition. Given any set A, we're going to define something called the power set of A. To be the set of all subsets of A. Okay, so for example, if you had a set A is 1 to 4, the power set of A would include everything that's a subset of that. For example, 1 as a singleton set, 2 as a singleton set, 4 as a singleton set. Notice the elements of the power set of A are themselves sets. You'd also have all the sets of size 2, 2, and 4. And of course, the entire set is a subset of itself, and, by the way, the empty set is a subset of all sets. So notice, just as a comment here, the cardinality of my original set is A. What's the cardinality or cardinal number of my power set? Well, 1, 2, 3, 4, 5, 6, 7, 8. My claim, by the way, is that when A is finite and the cardinality of A is some number m, sorry about that, then the cardinality of the power set of A will always be 2 to the m. And you can prove that pretty easily by induction. But I'm going to actually omit that here. I just want you to be familiar with the concept of the power set, because I'm going to come back to it in just a moment and talk about whether or not there are larger infinities than just the natural numbers. We know that the natural numbers is an infinite set, so it's got this transfinite number, but are there other transfinite numbers? So to talk about that, I'm going to do a little section here called the ordering of transfinite numbers. So my question that I want to answer through this section here is, which is larger? The natural numbers or the real numbers? We already know that the natural numbers are denumerable. And we also know that the real numbers are uncountable. So they're both infinite sets. One is denumerable, one is not. That is, it's uncountable. But which one is bigger? You probably already know the answer, but we're going to establish that formally. Okay, so recall, we've already said this, but I'm going to write it one more time as a definition. Two sets are the same size if and only if there exists a bijection F that maps S onto T. But we can also say S is less than or equal to T. That is, the cardinal number of those sets are ordered in this way. If we don't need a bijection, we just need a surjection. That is, we need an F that maps S, not a surjection, an injection, 1-to-1 to T. So T may have elements that don't get mapped to them from S, but it is 1-to-1. And if that's the case, if there exists this kind of function that is a 1-to-1 function, then we would know that the two sets are less than or equal to each other. That's S is less than or equal to T. However, I could write strictly less than or equal to by saying that the cardinality of S is less than or equal to the cardinality of T, and the cardinalities are not equal to each other. In that case, we would have that one set is strictly smaller than the other. And I wanted to say this because I want to come back and talk about the relationship of N and R in just a moment. Now, a few notes here that I'm going to put in the form of a theorem. If we let S, T, and U be sets, first of all, if S is a subset of T, then the cardinality of S is less than or equal to the cardinality of T, which makes intuitive sense and is actually not that hard to prove. We also know that a set's cardinality is always less than or equal to itself. Since the identity mapping is 1-to-1, that would always necessarily be true by definition of less than or equal to. Also, if S in its cardinality is less than or equal to the cardinality of T, and the cardinality of T is less than or equal to the cardinality of U, then just like inequalities hold with regular or real numbers, this what's called the transitive property also holds for cardinal numbers. That is, s then is less than or equal to u. D, if m and n are both natural numbers and m is less than or equal to n, then the cardinality of n sub m is less than or equal to the cardinality of n sub n. Now that's easy to prove, but it's actually true in both senses. It's true in the sense that we know the cardinality of m is m. The cardinality of this is m and the cardinality of that is n, so it's true by this. But it's also true in the sense that we can find a bijection. No, we can find an injection from this set here, right here, to this set here. There exists a mapping, darn it, from there to there. Okay, so E. Last point to be made. If S is finite, that is not S, sorry. If the set S is finite, then necessarily S cardinality is strictly less than Aleph null, meaning the cardinality of the natural numbers. Actually, I want to make one more point here. If the cardinality of S is Aleph null, meaning it is countably infinite, denumerable, the same size as the natural numbers, and T is a subset of S, which is finite, then necessarily T is also denumerable and has the same size as the natural number. So what this says is every infinite subset of a denumerable set is denumerable, which means that you can't have a smaller set that's still infinite than the natural numbers. So Aleph null is necessarily the smallest infinity, or what I would call transfinite number. But the question is there anything bigger than that? And that's where Cantor's theorem comes in. For every set A, there does not exist a surjection of A onto its power set. Remember, the power set is the set of all subsets. Now, what does this actually say? This says, essentially, that the cardinality of A must be strictly less than the cardinality of its power set. That the size of A is strictly less than the size of its power set. So we can always find a larger transfinite number, strictly speaking, by looking at the power set of a given set. So if A was infinite, then the power set would also be infinite, and its cardinality is larger than the original set. So that's strictly speaking. Now I want to prove this. Actually, it's pretty easy to prove by contradiction. Not by contraction. By contradiction. Alright, so what does the proof by contradiction look like? Well, what we're going to do is we're going to show that if we assume there is a surjection, it leads to a contradiction. So let's assume phi, which maps A onto its power set, is a surjection, meaning it's onto. So let A be any element out of A, which then implies that the output of my function phi is some subset of A, right? Since the power set is the set of all subsets, so phi of A is going to be something out of this set right here. So it's an element of the power set of A, which means it's a subset. Okay, so now that means either phi of A being a set, phi of A either has A in it or A is not in it, right? Because since phi of A is a subset of A, then either that element we start with is in there or not. So what I'm going to do is I'm going to create a set that's going to lead to a problem. It's going to be the set of all elements where A is not an element of phi of A. Right, so this function that's the surjection, whatever its output is whenever I plug A into it, I'm going to say let's let D be the set of all elements that A does not end back into its mapping. Now, note, D is a subset of A, right? And phi is a surjection, which means there's some element out of A such that phi of A naught is equal to that D. Something maps onto D. Okay, now if that's the case, either A naught is in phi of A naught, that is D, or A naught is not in D. It's either in there or it's not in there. But here's the rub. If A naught is in D, right, then by definition of D, A naught is not in D. Do you see that? Because remember, D is the same thing as phi of A naught, but to be in D means it's not an element of the set from which it mapped, right? Look right here. It's a set of all A's where A is not in phi naught. Well, A naught is not in, I'll even erase this down here so it's easier to see. To be in D means it's not in its own mapping. That is, it is not what you, it's not in the set that you get when you plug A naught into phi. And that happens to be D, so I just said if A naught is in D, then A naught is not in D. Contradiction. If A naught is not in D, notice that means that A naught is an element of D. By definition of D, it's the set of all things whenever you plug it into phi if A is in phi of A. Well, A naught is not in phi of A naught, which means it's in D, but that's a contradiction as well, which means it's basically a bunch of logic errors by creating this set that can't exist. That means that phi is not a surjection. Proved. Okay, so note, here's what we know. After all of that, the natural numbers, which are Aleph null in size, and the set of natural numbers has to be smaller than the power set of the natural numbers. So there is an infinity bigger than Aleph null. What's very interesting, and I don't have time to prove in this class, is that the cardinality of the natural numbers actually equals the cardinality of the reals, which we often denote in upper level mathematics as C. Okay, so this is a kind of a surprise here. We know from our previous proof that that's true. Now this is a little bit of a why, but it's absolutely true that the power set of the reals turns out to be the same size as, the power set of the natural numbers is the same size as the power set of the reals. Question: how many transfinite numbers are there? Well, we know that I can do this. Strictly less than or equal to. Now this is Aleph null. This is C. But are there anything bigger than that? Well, of course there is, because power set is a set. So I could take the power set of the power set, which would then be bigger. Okay, so this is, for lack of a better notation, this is 2 to the C. And why 2 to the C? Because remember, the cardinality of the power set is 2 to the number of elements in that set. But this would also be less than the power set of the power set of the power set of the natural numbers. So you keep going. So there are infinite number of transfinite numbers. But remember, we're talking about an infinite number of something. How many transfinite numbers are there? Are there Aleph null of them? I mean, is the number of transfinite numbers denumerable? Is it countable? Is it Aleph null? Or maybe it's C. Maybe it's an uncountable number, but it's the same as the cardinality of the reals. We know there's something bigger than that, but maybe it's bigger than that. The answer, that is an unknown problem. Sorry. In mathematics, we actually don't know the answer to that. Another thing we don't know is, does this exist? Is there a transfinite number somewhere in between there? The answer is unknown. Now, if you want to know what our conjectures are, our guesses are, I would leave you with this assignment. Google something called the Continuum Hypothesis, and you'll learn a great deal about whether or not such a number like this exists, and whether or not we think there are a countable number or an uncountable number of transfinite infinities. That is, are there an infinite number of infinities? Yes, but are there a countable infinite number or an uncountable infinite number? Whew, that's mind-blowing. All right, so that's the stuff I wanted to cover over cardinality and sizes of infinity. Enough to blow your mind, I hope, and with that, I'm going to leave off and stop there.